Chemistry is interested in what matter is made up of and how we can change its form. When we look at the smallest particle of matter, the concept of a limit to the smallest particles is pretty old, and that smallest particle is called the atom. The view of the atom keeps changing, and it will continue to change. It's not finished on our definition of the atom. But we have a very useful view of our atom now. It gives us lots of information. One of the earlier modern views of the atom was proposed by Dalton. He proposed that elements are composed of tiny, indivisible, indestructible particles called atoms. All atoms of an element are identical. Atoms of different elements combine to form compounds. Compounds contain atoms in small whole number ratios, and atoms may combine in different ratios to form different compounds. He had a pretty good view, except there are some differences with his view. We find that there are subatomic particles that we will describe, and we also find that not all the atoms of an element are identical. Another major development on our view of the atom came from Thomson, who did some experiments on cathode rays. We're familiar with cathode rays in terms of cathode ray tubes, which are the old-fashioned monitors and TV sets. Well, cathode rays were determined to be influenced by magnetic and electric fields. That's how we use them in our cathode ray tubes. The particle that was coming off of this cathode, so there's a cathode and an anode in a vacuum tube with a voltage, electrical voltage between them. And it's easy to boil off some type of particle, charged particle off the cathode. This particle is negative, and that particle is determined to be, or called, the electron. Using gases, we can get charged particles coming off the anode. And the smallest charged particle coming off the anode occurs when we have hydrogen gas present. That particle we call the proton. So this gave the view of the atom to Thomson of what's called the plum pudding model. It's a positive atom with negative electrons stuck in it. Rutherford modified this view with a nice scattering experiment using alpha particles, radioactive particles. He aimed them at a very thin gold foil, and then depending on the structure of the atom, we would expect different scattering patterns of these particles. He surrounds this with a fluorescent screen which is able to detect the alpha particles, and the results were a little surprising. Most of the particles passed right through the gold foil as if the foil was empty space. And then a small number were scattered at larger angle, and a smaller number were totally backscattered. So the view of the atom changed to be that there's a small dense center that we call the nucleus. And then surrounding the nucleus is something with very little mass, which we identified as being occupied by the electrons. The small dense center ends up having two particles in it, a proton and a neutron. So we have three particles in our atom now. Two of them occur in the nucleus, the proton and the neutron, and the electron occurs most of the volume. So the nucleus is what we call 5 orders of magnitude smaller than the atom. So the atom is 100,000 times larger than the nucleus. So our three particles now, we have electron, which has a negative charge. We have a symbol of E negative for that. Proton has a positive charge, is P plus for the symbol. Neutron is 0, no charge, so it's N0. So the proton and the neutron are located inside the nucleus, and the electron are outside the nucleus. Electron creates most of the volume of the atom, and when atoms meet, it will be the electrons that are interacting, not the nucleus. The nucleus contains almost all the mass. So the mass of the proton and neutron, we give a value of 1 atomic mass unit. And electrons are significantly smaller than that for mass. So the charge is this -1 for electrons and +1 for proton. We will not worry about turning it into a charge that we use on a macroscopic scale, the coulombs. The electron is what is interacting with adjacent atoms. So the electron is determining the electrical properties, or the chemical properties of the elements. For the neutral elements, for the elements which are neutral, this is everything that's macroscopic is neutral. So elements are neutral. So to be neutral, the number of electrons has to equal the number of protons. We find that electrons can be added or removed from atoms to form ions. So we will define our elements not on the number of electrons, but on the number of protons. So each element is defined by the atomic number, which is the number of protons. But the neutrons is not fixed. The number of neutrons is not fixed. So we can get different atoms that contain the same number of protons but different number of neutrons. We call these isotopes. So they will be the same element, they'll have the same chemical properties, but they have differences in the mass, and we can separate them based on those differences in the mass. So isotopes have the same number of protons, they're the same element, but they differ in the number of neutrons and in their mass. And at small elements, the number of protons and neutrons are about the same. But as we go up in mass on the elements, we end up with a larger number of neutrons than we do for protons. And isotopes also vary a little bit in stability. Some isotopes will radioactively decay into another element. When we want to talk about isotopes, we use atomic notation to talk about isotopes. We'll be using the symbol of the element. Lower left subscript will be the atomic number, and that's the number of protons. The upper left superscript is the mass number. The mass number is a whole number, just the sum of the number of protons and the number of neutrons in that isotope. So if we want to know the number of protons, it'll be equal to the atomic number. Number of electrons, if there's no charge, will be equal to the atomic number. Number of neutrons will be the mass number minus the atomic number. And just a couple examples of isotopes. For hydrogen, most of hydrogen is what is called hydrogen 1. It has 1 proton, 1 electron, no neutrons. Then we have a small amount of hydrogen 2 that can be found in the ocean. It will have 1 proton, 1 neutron, and 1 electron. And then there's a hydrogen 3 that contains 2 neutrons, and this one is radioactive and decays over several decades.